Welcome to VideoWissen. Elena Sacchi from the Leibniz Institute for Astrophysics in Potsdam did a talk in the series Babelsberger Sternnächte entitled A Simple Recipe to Make a Galaxy. So she deals with gas, dust, dark matter, and it will be really interesting. Stay tuned and have fun.
Hello, I'm Elena Sacchi and I work in the Milky Way and Local Volume Group at the EIP. And today we're gonna talk about galaxies and we talk about recipe to make a galaxy. Because galaxies are a bit like cakes, so you have some basic ingredients and depending on the way you combine these ingredients, you can actually obtain very, very different objects. But first of all, we can think about what actually a galaxy is. And I think, every one of us have a different idea of what a galaxy is depending on our background. So, of course, if you're a scientist, you will have a specific idea what it is. But people in history have had very, very different ideas for what galaxies actually are. And as the philosopher Bernard Deschartres used to say, we are dwarfs on the shoulders of giants. So I think it's very important to know and acknowledge the history of science, because the way we build new knowledge and the new achievements we can obtain are only possible because of all the previous scientists and researchers that came before us. So our ancestors' work is very important and is the basis for our new knowledge. Yes, already in the 5th century before the Common Epoch, Democritus, so he is famous for the atomic theory, proposed that the bright band in the night sky that was already known as the Milky Way might be composed actually of smaller objects, so of stars. And the word galaxy itself comes from the Greek galaxias, that means milky. So this is exactly because of the appearance of the Milky Way central band that is very bright, in particular in the southern hemisphere. And then later, the Persian mathematician and astronomer Al-Sufi made actually the first real observation of Andromeda and the Large Magellanic Clouds, which are two close galaxies to the Milky Way. So this was the first recorded observation of these external galaxies. And then later in the 14th century, Al-Jawiza proposed that the Milky Way, it's again a myriad of stars all packed together in a sphere of what was called at the time the fixed stars from Aristoteles. And then these stars are larger than planets. So this might seem like a very obvious observation to us. But if you just look at the sky, actually planets, in particular Jupiter and Venus, are much bigger than a star in their appearance. So it was not that obvious at the time that that star could be larger than planets or even different objects. And then later, just jumping to the 1600s, the Italian astronomer Galileo Galilei started to build and use telescopes to determine that actually this bright band we see in the sky at night is composed of stars, of little objects that we now call stars. So he was, for the first time, able to resolve the Milky Way into its components. And then we jump to Herschel. So William Herschel and his sister Caroline were able to count the number of stars in the night sky, and they start to describe the shape of the Milky Way and the position of the sun inside it. So here we can see one of the first sketches of the Milky Way, trying to describe this sort of disky shape and to model how the sun could move inside the Milky Way. And then we go to Edwin Hubble. So he's a very famous astronomer. So he was the first one actually to definitely put an end of a very big debate that was happening at the beginning of the 1900s. So actually some people argued that these nebulae that we were seeing in the sky were island universes, so objects quite similar to our Milky Way but external to it. While other people were thinking that those were just, these nebular objects, but like clouds inside the Milky Way. And finally, Hubble was able to measure the distance of Andromeda And he did it thanks to Cepheids. So Cepheids are variable stars whose brightness changes periodically, and they were discovered by the American astronomer Henrietta Leavitt in the early 900s. And she found a very, very important relation between the period and the luminosity of these stars. So the way the luminosity of this star changes depends on the luminosity itself. So this is one of the most fundamental laws we have to measure distances. So thanks to the work of Henrietta Leavitt, Hubble was able to measure the distance of Andromeda, or like trying to estimate it, and he saw that it was definitely too far away to be inside the Milky Way. So this was like the first definite proof that the Milky Way was not the whole universe, but there were other galaxies outside. And then also Hubble started to classify these galaxies based on their morphology. So mainly he classified elliptical, spirals, and irregular galaxies. And we can see this basic classification here in what is called the Hubble sequence. So we see on the left what's called elliptical galaxies, and these are roundish objects. They can be more spherical or more elliptical, and indeed we classify them on the basis of ellipticity, so how elongated they are. And then on the right, you can see two branches of spiral galaxies, so depending on the bar. So some spiral galaxies can show a bar at their center, so you can see this at the bottom. And also the Milky Way is one of these barred galaxies, while on the top we don't see a bar, but we see the same spiral structure, so a central brighter object that we call bulge, and then these spiral arms around the galaxy. And then, based on these findings, many astronomers started to work on the characteristics of these galaxies. So one of the most fundamental relations we have is called Faber-Jackson, and is the relation between the luminosity and the velocity dispersion of stars in an elliptical galaxy, and we will come back to this later. And then, similarly, Tully and Fisher found a similar relation between the luminosity and the rotation velocity of stars in spiral galaxies. And these two relationships are very important because, again, they allow us to measure distances. And then we come to more recent times. So this is the first Hubble Deep Field. So the Hubble Space Telescope was launched in 1990 and really revolutionized the field of galaxy evolution because it allowed us to go farther than any time before. And here you can see this beautiful deep field, and each object you see is actually a galaxy. So this opened really a window on how many galaxies are out there. And also, just to have a look at the image, you can see that galaxies are quite different. So you can see different colors, you can see different shapes. And of course, when you start studying them in a more quantitative way, you start to discover really a huge variety that we'll see later. And just last year, the first James Webb Space Telescope Deep Field was released, and opening even more to this field, because with JWST we can go even deeper, so farther away with the observations, and in a slightly different wavelength. So we can combine these two instruments and really continue our understanding of galaxy formation and evolution. And these steps are like very few ones, but in between there are many, many more people that worked on this and contributed to the field. And you can have a look at the full history of galaxy discovery and how we got to know what we know today. So we started with this basic classification, and actually this still holds today. So the two main types of big galaxies we see in the universe are indeed ellipticals and spirals. And they're quite different because ellipticals, not only in the shape, but also in the components they host. Ellipticals, they host mainly old stars, and typically have redder colors because of this. While spiral galaxies typically have bluer colors, and they host both old and young stars. And spiral galaxies, like the Milky Way, are mainly made of like this central component, the bulge, which is made of old stars. And then we have a disk, which we divide in thin disk and thick disks, but this is like this thin structure that hosts the majority of the young stars and the most recent star formation. And then around, we have this halo, also made of mainly old stars. And these spiral galaxies actually rotate in the direction of the disk, which is also something different from ellipticals, which instead have more random motion. So we call elliptical galaxies dispersion-supported, while spiral galaxies velocity-supported galaxies. But from the very first Hubble scheme, we went much, much further. And today we see really a huge variety of different galaxies, not only in the two categories we already saw, but we have completely new ones depending on the morphology and the luminosity. So, for example, we have a lot of irregulars, which, as the name says, don't have a very specific morphology, but they're more disturbed than indeed irregular. And also they host quite young stars. And then we can go into weirder objects. So as the research goes, we keep discovering new and new types of galaxies. So here are some examples. So here, for example, you see Horologium 1, which is an ultra-faint dwarf galaxy. And this type of galaxies host just a few thousands of stars. And they're actually the smallest galaxies we know today, and mainly located around other bigger galaxies like the Milky Way. While, for example, here on the top right, you see a low surface brightness galaxy. So this resembles a spiral galaxy, but with a much lower luminosity. Or we have shell galaxies, which are sort of in between ellipticals and spirals, because they're not very defined spiral arms, but these sort of shells around. And blue compact galaxies, so these are usually very active in forming stars in recent times. That's why they're so blue, and compact indeed, because their size is smaller than what we expect from their mass. And on the other side, ultra diffuse galaxies are actually bigger and more diffuse than what we would expect. And these are just a few examples, but as we go, we keep inventing new names and new categories, mainly on the basis of their morphology and the luminosity they have. But actually, the main components of a galaxy are the same for all these types. So the main ones are stars, gas, dust, dark matter, and a central black hole. So we're going to have a look at all of these components. First of all, stars. Here you see an example of what's called the Magellanic Irregular Galaxy, NGC 4449, because it resembles the shape and the properties of the Large Magellanic Cloud, and it's also an irregular. And here you see a map from Hubble Space Telescope of all its stars. And you can also see in pink the emission from the very active regions where stars are forming now. And this is, of course, the first component that was studied in galaxies because it's easy to observe in the optical wavelengths. And we actually study stars and the profiles of galaxies with many different tools. One of these is the surface brightness. So here you can see the profile of another galaxy, NGC 4459. So the surface brightness versus the radius from the center. And surface brightness is just luminosity measured in magnitudes, as we usually use in astronomy, divided by the area where we see this light coming from. And then we have gas. So this is the same galaxy as before, but you see the H1, so the neutral hydrogen emission map. And this is usually a much bigger component in space. So if we put the same image from before on top of this, it would be just the very central part. And the gas extends much further away in most galaxies. And actually, this is fundamental because it allowed us to discover dark matter. So here you see another galaxy, the Triangulum galaxy, and its rotation curve. So the velocity as a function of distance from the center. And actually, in the late 1900s, Vera Rubin made this discovery that looking at Andromeda galaxy. So she saw that the velocity of objects further away from the galaxy center was not going down as we would expect from just Newton and Kepler's law, but it was staying up, it was staying constant, or maybe going even higher. And gas is very important because since it's more extended, it allows us to measure further away and to confirm that this curve is just keep going constant or higher than what we expect. And actually this gap between the observed curves and the expectations is what made us think of dark matter. So this matter that is not visible because it doesn't interact in any way or with any kind of interactions we know, in particular not with electromagnetic interaction, but it's there because it's keeping galaxies stable and it's keeping these curves high. Now we have many more evidences of dark matter, but this was one of the first confirming that something was there that we were not seeing. And now we know that it's about more than 80% of the matter in the universe. And then we have dust. So any galaxy hosts these molecules around, so that it's called interstellar dust. There are residuals of supernova explosions and other molecules made of mainly metals and silicates. Just very small, like a few microns. So a micron is 1/1000 millimeters. And they can go from 0.2 to 50 microns, and they're all around stars inside galaxies. And a very interesting feature of dust is that dust absorbs ultraviolet and visible light. So here you can see, for example, the Andromeda galaxy in visible light, and you can see these dark stripes around the disk. But you see exactly the opposite vision when you go to the infrared, because dust, because of its wavelength, absorbs UV and visible and re-emits in the infrared. And it's very important to study, for example, the region where new stars are forming, because stars are surrounded by a lot of dust and gas clouds, so these are not accessible in the visible wavelengths. And this is also the power, for example, of JWST telescope, because we can observe in the infrared and really study these phenomena where in visible light we would just see dark spots. And then we have the central black hole. So here you see the black hole observed in the X-rays of the core of the galaxy M87. And this is something very universal to galaxies, unless we go into the very small and faint regime where we still don't have enough details and observations. But basically any galaxy hosts a black hole at its center. And you might remember recently also the beautiful image of the black hole of the Milky Way, Sagittarius A star. And these are quite different from stellar black holes. So stellar black holes are tiny, just a few tenths of solar masses, and they're the last phase of stellar evolution of very, very big stars. Well, in this case, we talk about supermassive black holes. So, for example, in the Milky Way, the black hole is 4 million solar masses, and they can arrive up to 10 billions of solar masses. So these are very huge black holes that just keep accreting materials. And actually, this is how we see them, because we see the material heating up around them and falling into the black hole. And last but not least, dark matter. So we already saw from the rotation curves of spirals that we can measure this amount of matter that we cannot see. But more recent techniques like gravitational lensing allowed us to make even more precise measurements. So here you see at the center what is called a galaxy cluster, because galaxies like to stay together, so they organize in clusters or groups. And in particular, clusters are very, very massive, so they're able to bend the light of objects behind them. And this is like a beautiful consequence of Einstein's general relativity theory, and one of the most beautiful confirmations of this theory. These sort of shells and stripes around are the images of galaxies behind this cluster that are being distorted by the gravity of the cluster itself. So we obtain images of the same galaxy in multiple spots around the cluster, and these images are distorted by the gravity itself, because gravity is, and a very big mass is able to bend light. To go back to the Milky Way, I think this is a very beautiful image of the Milky Way disk in different wavelengths, and this also tells us the power of observing the same objects with different instruments, because depending on the instruments, as we saw, for example, with dust, you can see different components of the galaxy. And for example, elliptical galaxies are surrounded by very, very hot gas that emits in the X-rays, or spiral galaxies are surrounded by neutral gas, neutral hydrogen gas that is very clear in the radio regime. So observing in different wavelengths allows us to sort of have a very clear and full picture of all the components inside the galaxy. And we already talked about a bit the relations that were found for elliptical and spiral galaxies, and just to show what they are in details. So for elliptical galaxies, we have the Faber-Jackson relation. So they found that the velocity dispersion, so the difference in velocity of different stars, is proportional to the luminosity of a galaxy. So here you see each point is a galaxy on the left plot, and on the x-axis you have magnitude, which is the logarithm of the luminosity, while on the y-axis you have the logarithm of this velocity dispersion. And so you see a straight line because we have a log-log plot, but actually the luminosity is proportional to the velocity dispersion times an index that is around 4. And the same or a similar relation can be seen on the right from spiral galaxies. So in this case, we don't take the velocity dispersion, but we take the maximum velocity. So if you remember in the rotation curve we saw of spiral galaxies, there is like a peak, so the maximum velocity, and the luminosity is proportional to this velocity, again, times to the power of about 4. And here you see like the same relation in different optical bands. But this relationship do not hold, for example, for other kind of galaxies like irregulars and dwarfs. And for this, we have other important relations like the luminosity metallicity or the mass metallicity relations. So basically, on the y-axis of both plots, you see what we call metallicity in astronomy, which is the amount of elements that are not hydrogen or helium. So everything that weighs more than hydrogen or helium, we call a metal. And here in particular, you see the ratio between oxygen and hydrogen. And then on the left, you see on the x-axis again the magnitude, and on the right, the stellar mass of each galaxy. And you see that up to a certain point, we have a very clear relationship between the two, which is quite important to understand how galaxies are able to retain their materials, for example, after a supernova explosion, which is a very powerful event that can expel materials out of the stars. But like big galaxies generally are quite good to keep those inside the potential of the galaxy. While, for example, if you see the color points at the bottom, these are all galaxies that are not following this relation, and these are very, very metal poor, as we call galaxies. And one of the reasons we think for very small galaxies is that these galaxies are so small that, for example, they're not able to retain all this material from supernova explosion. And then another reason actually could be galaxy interaction. So galaxy interaction is something very, very common in the universe, and there are many different kinds. So here you see just a few examples, but if you look around, there are so many different types of interaction. And they can happen between galaxies of similar size or between a bigger galaxy and a smaller one. And actually this sort of merging and interaction is what we think is happening from the beginning of the universe to create bigger galaxies. So we say we live in a hierarchically assembled universe, so bigger galaxies are created from the continuous merging of smaller objects. And for example, this interaction can also completely change the morphology of a galaxy, and we think that one way to form elliptical galaxies is from the merging of two spirals. So they can really affect the structure of the galaxy itself. In other cases, they can trigger star formation, so the interaction between galaxies can create some regions that will be able to form stars. Because the gas is getting compressed, and if the temperature and pressure go high enough, we can create new stars. Or even creating like completely new types of stars. For example, tidal dwarfs were quite recently discovered, and here again you can see some examples. So these are dwarf galaxies that are interacting with a bigger one. Because of this interaction, they become very dispersed, and they create this sort of long tails because of the tidal fields created by the interaction itself. And actually these sort of interactions in principle should happen at all scales. So even very small galaxies should have their own smaller galaxies that are merging with them. And this is something I studied quite a lot. So here you see two examples. NGC 4449 on the left, which is the same galaxy we saw before, and DDO 68 on the right. So these are two dwarf galaxies, and we discovered that their own satellites, so these other stripes of stars you see, or in the case of DDO 68, even the tail of the galaxy, we think was formed by the interaction with a smaller object. Even the Milky Way itself had many interactions, both in the past and in the future. So here's a stream of stars that we observed around the Milky Way, formed by an interaction with the Sagittarius dwarf galaxy, which is quite small. It was also quite small when the interaction started, but was able to form this beautiful stream of stars around the Milky Way that we can observe today thanks to telescopes like Gaia. And actually, thanks to Gaia, we're also able to reconstruct the history of how these streams were formed. So what we think happened is that the Sagittarius dwarf galaxy started to orbit around the Milky Way, and it had at least three very big interactions with the disk of the Milky Way. And we can see the signature of this interaction in the way that the Milky Way forms stars. So these three interactions trigger the star formation in some parts of the disk, and we can see the consequences of these interactions when we study the star formation history of the Milky Way disk. So even a small galaxy, like 10,000 times smaller than the Milky Way, can have a huge impact of bigger galaxies. And about future interactions, so we live in what we call the local group. So the three bigger galaxies are the Milky Way, Andromeda, and the Triangulum galaxies. And around we have a lot of smaller satellites. But we know now that Andromeda, which is at the moment about 2.2 million light years away from us, is actually falling towards the Milky Way. So we were able to measure the speed of Andromeda falling towards us at a velocity of about 100 kilometers per second. And we also measured what are called the proper motions of stars in Andromeda. So we measure the position of stars at an epoch, and we take the same measurements years and years later, and then we are able to see the velocity change of stars, for example, in this case, inside Andromeda. And thanks to this, we have like a scenario of what is going to happen to these two galaxies. So right now we see, you know, the Milky Way stripe and the tiny object here, which is the Andromeda galaxy. So if you're very lucky, you can see it with the naked eye. And then we think that what is going to happen is that, in a few billion years, they're of course starting to get closer and closer, and the sky also will change because we will start to see the effects of this interaction. So again, the gas will get compressed, so probably there will be new stars born at the places where this interaction takes place, and then this will keep going, creating beautiful sky with a lot of new stars born, until in about 4.5 or 5 billion years, the two galaxies will finally merge and create a new, probably elliptical galaxy. So what is going to happen to us is probably nothing, because galaxies, despite all the components we saw, are mainly empty objects. So they will just cross each other, and then, of course, the gas will interact, but the stars probably will not hit each other unless in very rare cases. And the two black holes will finally merge and create gravitational waves, but probably to the solar system is not gonna happen much. So just to summarize what we saw today, we saw that even we have some very basic ingredients that form all galaxies. By combining them in different ways, we can obtain very, very different results. And then each component is better studied in a different wavelength. So that's why we keep building telescopes, we keep building new detectors, because we need observations as varied as possible to study galaxies in a complete way. And then interactions are really, really fundamental for galaxy evolution, because they can completely change the characteristics and the morphology of a galaxy. They can trigger the creation of new stars, and they can even create new types, like the tidal dwarfs. And finally, galaxy evolution is really a key field to understand not only galaxies themselves, but the history of the universe on large scales, because at these scales, the only force that counts is gravity. And by studying the interaction and the characteristics of galaxies, we can learn a lot about gravity, like, for example, we saw with dark matter. And thanks a lot.